Welcome to Legends of Data and AI. Each episode includes inspiring and actionable data and artificial intelligence insights from global leaders across industries. Your host, Dr. Usama Fayyad, was the first Chief Data Officer at Yahoo and is Chairman of Open Insights and Executive Director of the Institute for Experiential AI at Northeastern University.
Welcome, everyone, to a new episode of our podcast, Legends of Data and AI. My name is Usama Fayyad. I am Chairman at Open Insights and Executive Director of the Institute for Experiential AI at Northeastern University. With me today is a very special guest, someone who's been at the heart and probably at the origins of an area that many people have heard about, deep learning, neural networks, etc. Yann LeCun. Yann is the Chief AI Scientist at Meta, formerly known as Facebook, where he has played many roles. He's also a professor in multiple departments at NYU. Hello, Yann, and thank you for joining us today.
Hi, Usama. It's been a while that we haven't seen each other.
Yes, indeed. And we're both in the same town or the same area. Yann, if we may start, your background is amazing and you've had great experiences. Maybe give us kind of the brief overview of how would you describe your background and how you got to where you are today.
Okay, so as you said, I'm a chief AI scientist at Meta, which means I have my own research group. I advise various research groups at FAIR. So FAIR is an organization I created at Meta 8 years ago. It used to mean Facebook AI Research. Now it means Fundamental AI Research. And it's part of a bigger organization of R&D on AI called Meta AI. And I split my time between this and NYU. So I also, I'm a professor. I have a research group here. I teach, etc. And I really enjoy having a foot in both academia and industry. They're very complementary, I think. Before joining NYU, I joined NYU in 2003. But before that, I was at NEC Research Institute for a short time. And then before that, at AT&T Labs Research. And before that, at Bell Labs. And that's all been in the New York area for the last 34 years or so. And my background is my undergraduate degree is actually in electrical engineering. My PhD is in something I cannot define. Call it AI if you want. But I'm not a real computer scientist. I'm no longer an electrical engineer. So I don't really know what I qualify as.
Okay, thank you for that quick introduction. And there's, Yann has many achievements, great number of publications, and has been one of the very influential folks in the world of neural networks. So Yann, let me start with some of my questions. You've been working on neural networks from the early days of perceptrons and backpropagations on multi-layer networks all the way to what we call today deep learning. In fact, you're one of the founders of deep learning as a whole area of activity and research. So you've seen before the popularity on neural nets in the 80s, they became very trendy. Then people in the community lost interest, I would say, during the 90s as other learning systems became more popular. Why did we not do or go after more complex neural network models before? What brought back the initial idea that more complex networks can address some really hard and heretofore unsolved learning applications?
Well, I think that history will have to be written by people who do the history of science and technology. I was kind of too close to the action to really have a completely unbiased view on this. But my guess is that it's a combination of two or three things. The first thing is, as you said, the second wave of interest in neural nets was between the mid 80s and the mid 90s, and interest started kind of dropping around 1995, 96 or so. And I think the reason is that this was before the internet, really, right? The internet started taking off as a communication platform, really, around that time, but a little later. And so this was before also the idea that companies could open source software. This was before there was a lot of data that was available. This was before there were GPUs or kind of relatively low cost systems to do high performance numerical computation. So the fastest machines we had at the time were basically desktop workstations that could do 10 megaflops or something like this, right? Maybe a little more, but not much more. So the combination of limited computation, no sources of large data sets, and an inability to distribute our tools, software tools, because open source was not the big thing, right, yet, certainly when you were working for a company, made it very difficult for academic groups, for example, to kind of work with neural nets, because you had to invest like a year writing your own deep learning framework, what we now call that. Leon Botou and I and a few others even before we joined Bell Labs and then later at Bell Labs, spent years basically developing something that you could think of as the ancestor to, PyTorch and TensorFlow and things of that type. That was a huge amount of investment for us that allowed us to kind of do things like convolutional nets and experiment with them and figure out how to make them work and deploy them in products even. But for anybody else, it would have been a huge investment to do this, right? It's not something you could write, in between two deadlines in MATLAB. So as a result, people kind of moved away from neural nets because it was just too difficult to make it to work, to get it to work. And then the type of data you could apply it to was basically either handwriting recognition or CR, or speech recognition. These were the only two things where you had relatively large data sets on which those things could work pretty well. Every other data source was very, very small and was tabular, in most cases, for which neural nets are not particularly good. So that, I think, is the thing. And then people lost interest and got the idea somehow that neural nets didn't work, which wasn't true, of course, or that there were only a few people in the world could make them work, which wasn't true either. It's just that we had the right tools. The right tools give you superpowers. So it took until the 2010s, essentially, for easy to use open source platforms that and smashing results that really kind of got people stop people from being able to ignore the good results that neural nets were producing. And by that time, there were large data sets and GPUs and everything. So
yeah, no, I mean that makes sense. Before we delve into kind of some of the issues with neural nets and deep learning and the methodologies, maybe we can start at a high level. Can you share a story or two on how machine learning / data science was transformative to an organization or business? Right? What do you consider kind of the really convincing use cases where you say, aha, because of this, machine learning and data science, should take credit for this big transformation?
Well, okay, this is perhaps a somewhat controversial topic, but probably the most important use of machine learning and deep learning in particular these days is content moderation on online services, social networks in particular. And I'm not just talking about Facebook or Instagram. It's also true for YouTube and Google search and Twitter and everybody else. Okay, and none of those services today would work without deep learning. So you take deep learning out of Meta or out of Google, the two companies crumble. They're literally completely built around it. All of the services are built around it. And that includes, things like, of course, and that includes Amazon too, by the way. So it includes things like, ranking of either search results or newsfeed, but also content moderation. So taking down objectionable content. That has made enormous amounts of progress in the last 2 years. And things like, understanding content, so you can match content with the interest of people, whether it's entertaining content or informative content or things like ads, which really powers most of the services today. So that's the biggest use that I can see today. Now, there's a lot of other uses of deep learning that have become really kind of part of the landscape, even though much of the public doesn't realize it. You buy a car now in Europe. Most cars in Europe come with a vision system that looks out the windshield, from behind the rearview mirror, and implement something called AEBS. That means automatic emergency braking systems. So these are basically, it's a ConvNet, a camera behind a ConvNet behind a camera, I should say, that looks out the window, and if there is an obstacle in front of the car and the driver does not react to it and doesn't brake, the car will brake automatically and avoid a collision. That reduces collisions by 40%, and it saves lives. It's a big use
those are great examples. In fact, many people are unaware of the fact that, inside the Google search engine, the heart of the ranking engine is a machine learning, the MLR algorithm, which in many ways, you're right. If we take the market value of Google as a metric, that's a huge impact. Most real applications of AI today are very much ML dependent, machine learning dependent, which of course makes them highly dependent on data and training data. And of course, a lot of the machine learning successes today are focused on using complex deep learning models. In your opinion, and I know there's no right answer here, what happens to the rest of AI?
Okay, well, I mean, there is a big debate, right, between various people who advocate various, classes of techniques. So it is true that deep learning today, most of the applications of deep learning involve sort of reactive, input-output functions, right? Show it an image, tell me, either produce a description or tell me what's in it, or just make a simple classification, or here is a sentence in, Turkish, here is a translation into French or English. And, that works really well, but it requires a lot of essentially labeled data, which is manually labeled, right? And one of the big revolutions, you could say, over the last 3 or 4 years has been a reliance on self-supervised pre-training. So basically, you pre-train a gigantic neural net to represent the data, but not by training it to solve a particular task, but by basically training it to fill in the blanks or do some prediction task. Okay. So take a piece of text, remove 15% of the words, and then train some gigantic neural net to predict the words that are missing. And in the process of doing so, the neural net learns a good representation of text independently of language. And you can use this for massive multilingual translation or hate speech detection in all the languages in the world or something like that, right? But what's missing still is the ability for neural nets to do tasks that require some sort of reasoning. So, humans are able to plan hierarchically, right? So if I want to, I don't know, go from, New York to Boston, that's a task, right? I can measure my distance to Boston, which would be kind of like a cost function I need to minimize. I have to decompose this into kind of sub goals. So one goal would be, go to the train station, catch a train, or go to the airport, catch an airplane, etc. And when I get to Boston, catch a taxi, right? How do I get to the train station from here? Well, I can go down in the street, take the subway or hail a taxi. To go down to the street, I have to get out of my office, walk out, take the elevator or the stairs, etc. And then, I can decompose this stack all the way down to millisecond by millisecond muscle control, informed by kind of local conditions. And we don't have AI systems that can do this today, that can sort of basically decompose a complex task into subtasks and kind of reason and plan ahead, using a prediction for, what the effect of an action is going to be. So that's been the topic of a lot of my research over the last few years, is like, how do we essentially give the ability to learning systems to reason and plan, but it has to be done in ways that are compatible with deep learning, which means everything has to be differentiable, all the cost functions have to be differentiable and things like that. So this is really connected with classic work in optimal control and what's called model predictive control. And that requires building machines that have some idea of how the world works. So basically, a system that you give it a representation of the state of the world at time t, and you tell it, I'm going to take this action, make a prediction about what the state of the world at time t+1 is going to be, so that I can propose a sequence of actions and then predict what the effect is going to be on the state of the world, and then measure whether it's closer to the goal I want or not. And perhaps by some search optimization algorithm, I can find a sequence of actions that will optimize my goal, minimize my costs, right? So that's the thing I've been working on, and currently that's really missing. So there is some hint that deep learning systems, if you make them really large and you train them with tons of data, exhibit some properties that look like they are able to reason. Okay, that's been the case for very large transformers trained on text or multimodal data. But and so the big question is, do you need explicit mechanism for reasoning, or of the type that I describe, or is it just a matter of scaling transformers and make them multimodal so they work on just any data? Strangely enough, perhaps, I place myself in the first category. So I think you need this idea of world models and explicit inference things. I don't think just scaling up transformers will get us there.
Yeah, no, it's good to hear that kind of that symbolic side of the AI, and I agree with you. No existing systems that can do it today, and we need to see the kind of progress we've seen in the world of deep learning to happen in that other world.
Right, but you mentioned symbolic methods. So what I'm describing, depending on your point of view, can be seen as symbolic or not. Okay, because there is no real symbol in the process I described. There is representation of the state of the world, which basically are vectors and contents of associative memory or tensors or whatever. Everything is differentiable. So that's what I mean by saying that reasoning needs to be compatible with gradient-based learning. If you do like classical symbol manipulation, symbolic AI of the type that the good old-fashioned AI, that is essentially discrete and combinatorial, and that's not compatible with deep learning. So I don't believe in this at all. Okay, I do believe in sort of a form of it where symbols are replaced by vectors, and then logic is replaced by basically differentiable functions, things like that.
Yeah,
but I believe in inference. Okay,
that's a great. Yeah, no, I understand that difference in philosophy, and it is a big deal and a big question. Let's take a moment to delve deeper into kind of neural networks and deep learning, but not too deep, of course. We need to keep it high level enough. There was much fuss in the theory community in neural networks in the 1980s about the fact that one single hidden layer is enough, and having multiple layers did not theoretically add to the representational power of a neural network. Yet in real applications, we see that multiple layers seem to make a huge difference in addressing the more difficult applications, of course. How do you explain this to people? Like it sounds contradictory, but what would be your view on your explanation?
Well, the thing is, I've been trying to explain this to people for about 25 years. So if not more, actually more. And you have to understand, when I was at AT&T in the mid-90s, I became a department head. And in my group was people like Vladimir Vapnik, who, of course, was, a big advocate of kernel methods. And, coming up with those arguments that, you can do everything with two layers, basically one layer of kernels where you compare your input with, your training samples. And then just one layer of linear combination. And it's all a matter of, maybe some kernels are better than others, but, it's just a matter of designing your kernel, right? And I had a very hard time explaining to him and to the rest of the machine learning community who was enamored with kernel methods that this was not sufficient. That this basically was essentially glorified pattern matching, template matching, right? You're comparing an input to a bunch of training samples, like nearest neighbor. And you do the smart thing of kind of learning a linear combination of the resulting scores to produce the answer. And my argument there was, yes, you can do everything you can approximate anything with this. The same way, you can approximate anything with a two-layer neural net where the first layer basically is fixed and random. But it's very inefficient. There's going to be a lot of situations where this is possible, but incredibly inefficient. If you have a very large data set, kernel methods basically, grow with, with a third power of the complexity grows with a third power of the size of the training set. You're going to have to use tricks, to kind of make that more efficient. If you have a neural net where the first layer is random, this may work for like relatively small data sets of tabular data, but you're not going to do object recognition with this. So I had to explain to people, when you write a program on the computer, the number of sequential instructions you have to write is always more than 2. Okay, there's very, very few things you can do with 2 sequential instructions, that you can parallelize all the first instructions, right? And basically a 2-layer network is a program that has 2 instructions, okay, 2 sequential instructions. When you are a circuit designer, you're designing a circuit like to basically add, do things like add 2 numbers or determine if you have a even or odd number of bits that are on in a thing. You can do it with 2 layers, but for almost all binary functions, Boolean functions, the number of functions you need in the first layer is exponential. There's only a tiny number of functions for which it's not exponential. So for almost any function, certainly adding numbers, you need more layers than 2. So, I mean, there's tons of arguments. And actually in the mid-2000s, Yoshua Benjo and I wrote a paper where we were trying to explain all those things, right? You need multiple layers. And people knew this since the 60s, right? The people working on the perceptron knew that ultimately to go beyond the limitations of the perceptron, you had to have multiple trainable layers, which is why, I got interested in this when I was still an undergrad, right? In the very early, early 80s, like 1981 or 82 or something like that. That's when I started getting interested in multi-layer neural nets that nobody was working on anymore by that time, except Jeff Hinton and a few others. But it's a very natural concept. There's also the concept that to be able to do things like object recognition, you need to essentially have a system that can extract abstract representations of the data that the system handles. That's kind of the constructing abstractions is really what human intelligence is about. And when you have a system with multiple layers, you can see the intermediate layers as learning abstractions of the inputs, where the juicy parts are preserved and the irrelevant details are eliminated. Okay, it's connected with also notions of invariance, invariant representations, and things like that, right? So that was completely obvious to me, and I could not understand how people could not, understand or accept that. And that's what convinced me and Yoshua Benjo and Jeff Hinton and others that eventually this was going to win out, because like I couldn't see any other way to do it.
Yeah, I mean, you said it well. I mean, it's while the representation may be powerful enough, it's not a convenient or practical representation, and you're kind of over limiting yourself with a problem that becomes much harder. A question related to that, complexity in the input layers when you're doing a deep learning model, and kind of exploding that input space is often credited with the power of the deep learning models, but many also say it's actually the depth of the layers that is important. Which do you think is more important? If you were to pick one over the other, and I know the natural answer is both, or I think, which would it be?
Width versus depth.
Yes.
It's a trade-off. It depends what your criterion is, right? So, and there is some sort of optimal kind of trade-off between the two. You can, the same way in circuit design, if you design an electronic circuit, like you want to design, I don't know, a circuit that's going to add 2 8-bit numbers, you can actually do it in 2 layers. It's ridiculously expensive in terms of size of your circuit, but you can do it in two layers. It's going to be really fast. It's going to occupy a gigantic piece of silicon, but it's going to be fast. At the complete other end, there's a way to design an adder which is completely sequential, right? Add the first 2 bits and then carry, carry the carry, propagate the carry, and then add the next 2 bits, propagate the carry, etc. You need at least, some constant times 8 layers if you have 8 bits, right? And then you have all kinds of things in between that sort of predict what the values of the carry will be. And so they require a bit more layers, and they are a little faster, right? They're a bit more layers than 2, and they're much faster than 8. And then there is just a trade-off where things are just optimal, right? And that's what circuit designers use. It's the same with neural nets. You can make it shallow. You'll get the answer with very low latency, but then your middle layer is going to be so large that you're going to spend a huge amount of computation and memory on it. And then but learning is going to be easy. Or you can make it narrower and deeper, and then the latency is going to be higher. Memory is probably not going to be much cheaper, maybe a little bit. And what has been surprising, I think, over the last 10 years or 8 years or so is, since ResNet basically, is that you can actually have many, many, many layers, and it helps. It used to be that neural nets had 3, 4, deep learning was deep starting from 3 layers, basically, right? So, convolutional nets of the type that we used in the late 80s, early 90s had something like 7 layers maximum. And they were the deepest that, anybody were using at the time, other than like recurrent nets and things like that. But what happened, around 2015 is that we realized, you can build neural nets so that they have 50 layers or 100 layers, even more, and backprop will still work if you do it right. If you use ReLUs, if you have, skip connections and blah, 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 right? The ResNet style architecture. Or if you use canonical circuits that involve like things like associative memory type circuits, which is what transformers are based on. Yep. So that's been kind of a conceptual revolution. The one that occurred before is a conceptual revolution that people in machine learning were very, very resistant to for a very long time. Is the idea that you can train an absolutely gigantic neural net that has more parameters than you have data points, right? Many more, and it still works. Every textbook in statistics will tell you this cannot possibly work because you have so many parameters, you're going to overfit, right? And if you've done logistic regression or linear regression, you'll have to regularize, or kernel methods, right? You have to regularize to get good results. It turns out neural nets have this kind of weird self-regularization property that you can train gigantic neural nets that are way over parameterized, and they will still generalize pretty well. Why? We're starting to understand why, but I don't think it's kind of fully figured out. We knew this empirically from the early days, but we could not convince anyone who had read all those statistics textbooks that this was the case.
Yeah, and in fact, we are living now in an arms race where, the releases by Google and others, we're now in the hundreds of billions to trillions of parameters over
Right.
limited data sets, which is, crazy in the world of classical statistics.
Yeah, my colleagues at FAIR just released a 175 billion parameter language model, similar to GPT-3, with the difference that it's open source.
Yep.
It's called OPT 175B.
So, indeed, it's hard to keep up with the numbers. So, how, that brings up a related quick question, and then we'll go to other topics. So therefore, if you're a practitioner and you're trying to decide on a network architecture, how do you start a new problem? It seems like there's a lot of art and design when it comes to kind of laying out the network. How big do I make the input space? How many layers deep? How do I design that depth? Is there a systematic approach to getting there, or are we still kind of in the art and blind search world?
Well, it's not blind search. It's called engineering, right? So, any creative design activity, whether it's in engineering or art or design of any kind, right? Architecture or whatever, is a combination of creative insight and intuition supported by, technical knowledge and scientific evidence. And so, we have this mental model of how those deep learning systems work, and that is what directs our intuition of how to design an architecture for any particular problem. That space is somewhat kind of constrained by sort of general classes of architectures that people have experimented with and and gotten the results with, right? So if you have natural data that comes to you in the form of a multidimensional array that has local correlations between nearby variables, and that the statistics basically are the same regardless of where you are in the array. So whether it's images, audio, video, whatever, multispectral images, whatever it is, it's a good idea to use convolutional nets, okay? At least for the first few layers. By the time you get to a certain number of layers, then what the system represents basically are objects. You can think of it this way, right? So then you have to do some reasoning that is object-based, okay? I have this image, there is a car in front of a pedestrian, and it occludes it partially. So how do I figure out, like, is it a car and a pedestrian, or is it something else? So you need to do some object-based reasoning, and for this, transformers are really good. So my favorite architecture for detection, for example, localization, is inspired by some work by a guy called Nicolas Carillon, who was a resident PhD student at FAIR Paris until recently, and now he's a postdoc with me at NYU. Called DETR, D-E-T-R. That means basically detection transformer, and basically it's a convnet followed by a transformer, where the transformer does all the object-based reasoning essentially, and you can train it end to end to do detection. It works really well. There's been follow-up work on this that I think are really interesting. So that's kind of my favorite way to approach that problem. Now, what if the input data you have does not come to you in the form of a neat array? So first of all, if the input consists of discrete tokens, like text, then you may not need the first few layers of convolutions. You might get away with just plugging a transformer directly on the input, and that's what current NLP systems do. But then what if the data that comes to you is not, doesn't have kind of a neat geometric structure where, nearby values are correlated? Let's say you have a bunch of, I don't know, financial time series. Okay, how are they related? Maybe there are two, I don't know, stock values of two companies that are in the same market, and so they are correlated. So for this, you want to use something called graph neural nets. And transformers basically are a way to do graph neural nets that are dynamic and basically automatically learn. So they sort of subsume this idea of graph neural net to some extent. Where with the attention mechanism, you can put in relation to variables that are correlated and need to be kind of combined.
I agree. It is. I mean, there's still a lot of kind of design there, and design is an essential part of engineering solutions.
It's engineering.
Yeah. So let me switch gears here, and there's a lot of talk, and in my opinion, hype about AGI, artificial general intelligence. And let me start with the short question of kind of, what do you think about this? This is AGI, achievable? And maybe a related question to that is, what do we need to get there if we're going to make our way there through deep learning or otherwise?
Okay, so let me first say that there is no question in my mind that human level intelligence, in the sense of a machine that would have, similar or superior intelligence to humans in all the domains where humans are competent, okay, is possible. There is no question we'll reach that point at some point, okay? How long is it going to take? I have no idea. It's not going to be tomorrow. It's not just around the corner. And I think we need, conceptual breakthroughs before we get there, perhaps of the type that I was mentioning earlier, machines that can, learn models of the world and, can do prediction, long-term prediction, and learn abstract representations, things like that. But and do long-term planning and hierarchical planning. So, we're not going to get there tomorrow, but there's no question in my mind that it's possible. Now, I call this human level AI because, or the threshold where we pass that stage is human level AI. I don't call it AGI. I think AGI is a misnomer, because I do not believe that human intelligence is anywhere close to general. We think that we have general intelligence, but we don't. We are extremely specialized as humans. There are many tasks that are seemingly intelligent tasks, that computers do much better than us. Even the current crop of computers can do much better than us. Even the current crop of computers that are not seen as part of AI, okay? Like just doing arithmetics or computing logarithms or whatever, like solving differential equations, numerically. And then there's playing chess and Go and things like this, right? So I mean, computers are just much better than humans at this, and what that shows is that we're not that general in many ways, and there are tasks that we cannot even imagine. They are complete. We think we are general because all of the tasks that we can imagine are those that we can imagine solving. But in fact, the number of such tasks compared to the total number of all tasks is absolutely tiny. So there are many more tasks that are completely unfathomable to us that we can't even imagine beginning to solve.
Yeah.
Human intelligence is
very I think our views are very biased by our own perception of what the world is like, because that's the only intelligence we know as kind of looking at it without glass. Yeah.
And by what we perceive as being the structure of the world, there's a lot of structure in the world that we just cannot perceive. It's just way too completely outside of the type of things that our brains are able to model.
So something more mundane, right? I mean, one of the big concerns, as we get successful applications of deep learning and machine learning and so forth, people become more and more worried about biases of algorithms. How do we get deep learning models or can we get deep learning models to become aware of bias? And can we get to a state where a deep learning model kind of starts showing awareness of bias and figuring out how to mitigate against it? It's a kind of a very fuzzy area.
Well, it's an important area for sure. A lot of my colleagues at Meta generally and at FAIR in particular are really interested in this. There is an entire organization that is part of Meta AI called Responsible AI that basically just focuses on that, but also researchers at FAIR, including people like Léon Bautou, my old friend Léon Bautou, whom that who also kind of are really interested in that question. So the one issue there is what are the how do you define bias, first of all? Can you completely eliminate bias? And the answer is probably no. If you eliminate completely bias, you also eliminate all the information you have in your data set, right? So you can mitigate bias, you can find good trade-off between limiting bias, minimizing bias, and actually solving the task. You can certainly pay attention to inherent biases in your data. And there is a lot of ways that data can be biased that people are learning about. There's a lot of uses of deployed machine learning systems that create biases that people also are learning about. In fact, I thought this was so important several years ago that together with Eric Horvitz and Demis Hassabis and a bunch of other people, we decided to create the Partnership on AI. So that's a large group of partners. This is with there's over 100 partners now that from the industry, academic world, NGOs, government organizations, etc. Basically, it's a forum to discuss like how do we make sure that the deployment of data-driven machine learning AI systems benefits society essentially, right? It doesn't have like deleterious side effects. Because all of the large companies have been bitten at some point by some system they deployed that turned out to not work the way they thought it would, or turned out to have some bad side effect. Sometimes was caught in time, sometimes not, right? And when it's not, then it creates some sort of scandal and hurts people. So you have to be careful, like can we exchange tips in the industry and among researchers as to what's the proper way to deploy data-driven machine learning AI systems so that they do the right thing. And there's no simple answer to this. It's a complicated issue.
Yeah.
A lot of people are working on it.
I mean,
it's front and center for companies like Meta, of course. Because
and related to responsible AI, and maybe is the whole issue of explainability to humans. How do I, part of getting trust into a model or what a machine is doing is for me to get a mental model of what it's doing, and therefore requiring me to kind of understand or explain why the model is making these decisions, which also kind of relates to an even deeper issue. The whole regime we're in is we have to train these models on data, and therefore we have to rely on the fact that the data is going to contain every possible combination that we might encounter in real life when this system is online and running. Yet that's impossible. And one of the issues that worries a lot of people is, what does a deep learning model where I don't understand what it's doing as a human do when it faces a new combination of inputs that it hasn't seen before? What can you say about its outputs? How do you kind of get it to realize and control that, hey, I haven't seen this before, my certainty is low, and therefore I need to do something different? What do you think about all these topics?
Okay, I have a very unorthodox position about this. I think explainability is considerably less useful than people think it is. So I've had the experience multiple times in the last couple of decades where someone would come to me and say, it'd be great if you could use a machine learning system to solve this particular problem. Okay, make this prediction. It doesn't matter what it is. Okay, and they look at you in the eyes. I'm sure you had this experience too. They look at you in the eyes very intensely and they say, we absolutely need that system to be explainable. We need to understand exactly what it does, right? Okay, and then you go out and you build two systems. You build one that basically is something like logistic regression, completely explainable, okay, easy to understand, all right, which gives you, I don't know, 70% correct, right? Some measure of correctness. And then you build another, gigantic neural net that gives you 95% correct. And you propose that system to the person who came to you and just before looked at you in the eyes and said, it's very important that the system be explainable. Every single time, that person will take the 95% non-explainable system. Every single time, right? So despite the fact that they think explainability is important, which is basically a way of reassuring themselves and their colleagues that the system does the right thing, they don't actually care about it. The only thing they care about is testable performance. And this is true not of just machine learning systems. This is true of, I don't know, medicine, drugs, right? There's a lot of treatments that are completely standard treatments for, various kinds of ailments where the mechanism of action is not very well understood. How is it that lithium can treat bipolar disorder? Basically, we have no idea. We still use it. So I think the ultimate solution to trust is thorough testing. And this is what we do for everything that has, that is life critical, right? We don't, I give you two options. There is this new airplane that was just built and it was simulated to death. And there was, some theoretical proof that, it's very safe and it's never going to crash and blah, 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 but it's never been tested. And then this other airplane, has been, built the usual way by a bunch of engineers who know what they're doing, and maybe not, no theory to support it or anything like that, but it's got, thousands of hours of flight and it's been thoroughly tested and everything. Which one do you fly on? I take the second one. So ultimately, you need trust, and trust comes from thorough testing. Now, it's true that for things like autonomous driving system, you cannot possibly test an autonomous driving system in all situations it will ever encounter. And the question is whether you can test it to the degree that it will be more reliable than a human driver by, let's say, a factor of 10, right? And human drivers, cause fatal accident once in every, 150 million kilometers or something like that. So that's a lot of testing, okay? But that's the way it's done with drugs. That's the way it's done with airplanes. That's the way it's done with just about everything. No proofs or explainability will, do anything to reassure people. At least it won't convince me. Now, there's a second question to explainability, which is that when a machine learning system makes a decision about that is important for people's lives, like, are we going to give you this mortgage or something? What you'd like is the system to be able to make actionable suggestions as to what the person might do to, change the decision from negative to positive, right? And that we can do with neural nets. I mean, we can do gradient descent in input space and figure out what's the minimum perturbation of the input variables that I should do to flip the decision, right? So that's explainability. You can do this with neural nets or with anything, any model, or at least differentiable models.
So I'm aware of the time here, and we've definitely, I have so many more questions for you. So let me end it with one last question, if I had to choose. And this is the whole topic of that a lot of people care about, which is kind of the energy consumption of, the training phase of a deep model, and sometimes the use of that deep neural network model versus, compared to how the human brain or even animal brains do the processing at a much lower levels of energy. How do we address this issue of, excessive energy consumption and computation? Is there an answer to that?
Well, the excessive power consumption has nothing to do with whether it's neural nets or anything else. It has to do with the state of our fabrication technology. Okay, so our 5 nanometer CMOS transistors, if you want to flip a bit, a line or something like that, right, consumes a certain number of joules, and until we find a completely new technology or we further reduce the size, which we can't basically do. I mean, Moore's law essentially has stopped. This is not going to get much better than this. So so we have to look for completely new technologies. I don't know if it's spintronics or carbon nanotubes or whatever, but that's going to take a while. It doesn't exist yet. Then it doesn't matter whether you run neural nets or deep learning or whatever else on top of it, right? I mean, it's just the state of fabrication technology. Now, on top of this, there is is it more efficient to use neural nets or something else? And we don't have any alternatives at the moment. So this is not a question for which there is an answer you might like. We have to use neural nets. We don't have anything else if we want to do vision or anything else. Now, are people working on trying to minimize the energy consumed by neural nets, either for training or for inference? And the answer is yes, because there is an enormous incentive for companies to do this, because it consumes a lot of electricity, and you want to have some intelligent virtual assistant that lives in your augmented reality glasses, and that doesn't run out of battery in 2 hours. And so there's a lot of people working on this, like a lot of people, and a huge amount of money invested into reducing the energy consumption of neural net inference, for example. Same in data centers, right? I mean, you have enormous data centers, as I said before, operations of Meta and Google and everyone else use deep learning at a very large scale, and the networks are getting bigger and bigger. And so there's an enormous incentive, again, to have specialized hardware architecture that allows you to do inference really fast. And this is really where all the energy is consumed. Now there is the question of what about training? And frankly, the training part of it is a tiny portion of energy consumption. So people who worry about the fact that, training, large language models consumes as much as, I don't know, a third of, a round trip to New York by, a modern airplane. You don't do this every day. So, the direction of history now is that, you train gigantic models that can do everything in one model, right? They can do NLP models that can do, translation, hate speech detection, and everything else, or, topic classification, basically with one single neural net that works for every language. and you only pre-train it once, and then you specialize it for all the tasks that it needs to do, but you pre-train it only once. And maybe that costs about, some fraction of round trip, from New York to Paris on a jet plane, on an airliner. But then you do this, once in a while, maybe every 6 months or so. Now you have to realize, how many transatlantic flights are there per day? It's 1,700. So the amount of energy, spent into training models is basically negligible. I mean, it's basically nothing. Like in the grand scheme of things, it's nothing. Now you have to realize also the entire IT industry, which includes data centers and telecommunication technology, all that stuff, right? That's about 6 or 7% of all energy consumption across the world. So that's a relatively small part. Within this, machine learning inference is a small portion, maybe 20%. That might grow to 50 or something like this. Within this, training is a tiny portion. Okay. And then there is the question, is it going to grow exponentially as we go? And the answer is no, because and in fact, our friends at Google have a paper on this. They show that the growth of, the energy consumption that would be devoted to kind of AI systems over time is basically going to stay constant, even decrease slightly, because of progress in specialized hardware, because of progress in software, but also because the upper limit of what we can spend in terms of energy on this is limited by economics. Okay, you cannot spend too much on computation because then your service becomes economically infeasible. So, we're not going to have some ridiculous, exponential increase of computation there. We're going of energy consumption. There's going to be an exponential increase of computation because computation becomes exponentially more efficient.
Affordable, yeah. Agreed. Yann, thank you for taking the extra time. Thank you for sharing your wisdom and knowledge about these thorny and actually deep issues here. We very much appreciate it. Thanks for joining us today.
Thank you for having me. That was fun.
Thank you, everyone, for listening to this episode. And I look forward to seeing you in a future episode of Legends of Data and AI. This is Usama Fayyad with Northeastern University and chairman of Open Insights. Thanks, everyone.
Thanks for listening to Legends of Data and AI. We hope you enjoyed our deep dive into the world of data and AI. If you're keen to learn more about making data and AI work in the real world and in any organization, join us next episode and subscribe to the podcast. As always, you can head over to open-insights.com to sign up for our email list, learn more about the work we do, and have access to data resources. See you on the next podcast.